Okay.
Recording here. So very good evening class. Thank you very much for coming for the replacement class. Feeling much better. So we are going to continue with our chapter 2 lesson. So yesterday we actually learned the lesson about instruction logics, and we saw how to actually apply them for certain operations, especially when we saw how to clear the bits, how to set the bits, and so how to toggle the bits. And we saw application of logic in order to filter out certain numbers. We saw in our example that how to actually find out whether a number is multiple of 8 or not. Or in that case, we actually use logic instructions to filter out which elements actually have multiple of 8. So, if you see the coding was actually a combination of table pointer and also logic operations. Now that actually, to illustrate that, whenever you do a program, you will be using a lot of whatever knowledge that you have learned before in one program. So likewise, the same thing goes also with your take-home quiz, where you need to use table pointer and certain other things you have learned. So like that, you need to incorporate all those different elements of knowledge that you learn in order to achieve the task, or whatever given task that is given to you. So we're going to continue with the next element, which is one of the important and most useful element, which is using programming loops to create time delays. Have you seen time delay application before? Practically it's everywhere. Everywhere there is a time delay. Your watch has time delay, your traffic has time delay, everything has a time delay. So we're going to see how can we actually create and generate the time delay. So very simple application of time delay you can see is in traffic lights. Right? The red light actually will be turned on for a certain period of time, and then the orange and then the green. The green also will be on for a certain duration of time. Nowadays you can see the traffic lights with the 7-second display. Right? You can see how long the green light will be on, so on and so forth. So we're going to see how that element of creating the delay is actually very important, because you can't escape it. You can't escape from not using delay in daily applications. So we're going to learn how to actually create a delay. So the PIC 18 actually uses a crystal oscillator or RC circuit. What is RC? What is RC circuit? Resistance capacitive circuit. How does resistance capacitive circuit generates oscillation? You have learned about oscillation circuits, right? I don't think so, you all have learned. So to generate the clock signal needed to control this operation, the crystal oscillator, it looks like a capacitor. It uses crystal. So it provides the oscillation. You take a oscilloscope and you put at the legs of the crystal oscillator, and if you, nowadays most of the oscillator are actually digital, so you can see the square wave, the sinusoidal signals. It generates a frequency, particular frequency. And everything runs on a particular type of frequency. So you can generate frequency from natural elements, for example like crystal, and generate certain types of frequency, or you can generate it through electronic circuits. RC circuit, then you can generate the output signal. So have you seen your watch? It's the old watch, you see at the back it returns quartz. Never seen your dad watch lah. Those old watches they use crystal to generate the basic frequency. You need a base frequency so that you can work on that frequency. So anyway, that's not our subject of study. So the instruction execution time is measured by using the instruction cycle clock. So the term that we'll use here is instruction cycle clock. If you see in your instruction set, for each instruction there is something on the third column is mentioned cycles. You mention how many cycles that one particular instruction takes. So that cycle is known as the instruction cycle. How many cycles it actually takes. And there is a timing for every cycle. Like for example, if you see the first instruction ADDWF, cycles is mentioned 1. So that means in order for the microcontroller to execute that ADDWF instruction, it takes 1 clock cycle. Do you understand the term? That's what it means. One means it takes one clock cycle. Sorry, one instruction cycle clock or whatever. Good terms. So we need to find out one instruction cycle takes how long. Now one instruction cycle is equals to 4 times the crystal oscillation clock period. So this is how you will find out that one instruction cycle, because here we are dealing with instruction cycles, right? So one instruction cycle is equals to 4 times the crystal oscillation clock period. So in that way, you can find out that this one cycle takes how long. The reason why we actually wanted to know one instruction will take how long is because we will repeat that instruction to create a particular time duration, a delay. So a desirable time delay is created by repeating the chosen instruction sequence for a certain number of times. So rather than going through this instruction, going through this notes, we'll see an example. Write an instruction sequence to create a time delay of 500 milliseconds. The PIC18 is using a crystal oscillation of 40 megahertz. That means the crystal is actually using a crystal at this frequency. And the frequency crystal is actually 40 megahertz. So what we're going to do now is, we're going to write an instruction that will generate a time delay of 500. This is our oscillation frequency. So usually in the time delay, they need to give this oscillation frequency. So which crystal that you are using. So we're going to see one. in our instruction set, the column mentioned about cycles, right? That is this. This is one instruction cycle. So when we say instruction cycle, this is one instruction. So now what we want to do is we want to find out one instruction cycle, what is the duration of this one instruction cycle? How long does it take? So the duration means how long is this one instruction cycle is equals to 4 times the crystal oscillation period. Now, is this period or frequency? This is frequency. If you want to get the period means? Yes. So, it's actually 4 times 1 over frequency oscillation. This is given, right? This is given. So, 1 over 40 mega. What is the value? What's the nearest?
100 nano.
Yes, 100 nano. So it means when you execute that ADDWF, it takes one clock cycle, one instruction cycles, right? One instruction cycles, if your PIC is running on this frequency, that means the one instruction clock cycle will take 100 nanoseconds to execute. So that one instruction cycle takes 100 nanoseconds. Are you all following up to this point?
Oh.
So now since we know the basic one instruction cycle takes this 100 nanoseconds, now we're going to create a basic time block. So what is the need of creating a basic time block? Okay, this is one method, then later I'll show another method. So this basic time block, so first how we're going to approach this is we're going to create what do I mean by a basic time block is that what is the basic time of your watch that you're wearing? 1 second, right? 1 second is the basic time. Based on that 1 second, you multiply to get 1 minute. How many times you need to multiply? 60. So that is the understanding of the basic time block. So we're going to create a basic time block of, let's say, a time block which is small enough. This is for example. So let's say we're going to create a basic time block of 2 microseconds. Why we need to create a basic time block is that, you'll see in a while. So if you want to create a time block of 2 microseconds, how many instruction cycles do you need? If this is the time block that we actually want to create, 2 microseconds, if we want to find out
20.
how many instructions do we need?
20. Yes.
Okay, one instruction cycle takes 100 nanoseconds. Understand that? Now, if we want to create a basic time block of 2 microseconds, how many instruction cycles do I need so that I can achieve 2 microsecond delay?
20.
20. How do you get 20?
2 micro divided by 100 nano.
Yeah.
No, I don't.
quite simple thing, right? If one instruction takes 100 nanoseconds, if you want to find out how many instruction cycles that you need, just take the time that you want, divide by 100 nanoseconds, you'll get how many instruction cycles that you need, right? Don't worry about writing. Understand what's happening here. So how many instructions do you need? 20 instruction cycles. Do you all get the same number? Again, don't worry about writing. Worry about understanding. So whenever we do the calculation, make sure all of you do the calculation, so that you understand. Don't worry about writing. So, in order for us to have this 2 microsecond delay, how many instruction cycles do we need? We need 20 instruction cycles, right? So how can we actually achieve these 20 instruction cycles? We're going to use NOP instruction. If you see NOP has how many instruction cycles? Can you check? NOP. It takes one instruction cycle. So if in my program, if I write 20 NOPs, this whole NOP is equals to 20 instruction cycles, right? So for the PIC to execute these 20 instruction cycles, how long does it take?
2 microseconds.
What's that?
2 microseconds.
2 microseconds. Just this advanced, right? So this whole thing takes 2 microsecond delay to execute. So basically what we're doing, we're wasting time now. Just put this NOP instruction. Do you all follow what we're trying to do now? Of course we have not got into the picture yet. Do you follow what we're doing? So what we are trying to do is we are trying to create a basic time block. As if like 1 second, right? We're trying to create a basic time block of 2 microsecond delay. So we have successfully created a 2 microsecond delay. So this is our basic time block. Do you understand how we get this 2 microsecond delay or not? Each instruction takes, this NOP takes 1 instruction cycle, right? And this 1 instruction cycles actually takes 100 nanoseconds. So if you want to find out how many cycles that you need to create the 2 microseconds, you just divide. So you need 20 instruction cycles. So if you write NOP 20 times, the time it takes to execute all this is 2 microsecond delay. So we're going to use this as a basic time block, and we're going to multiply this to generate our required time delay. You all follow? So if this is our, for example, like I am asking you, in 1 minute, got how many seconds? So you actually do the calculation, you get 60, right? That is because you are using the basic time block of 1 second. So now we're going to generate this 2 seconds is our basic time block. So we're going to find out that in order for us to create 500 millisecond time delay, how many times do we need to loop this 2 microsecond delay? How many times we need to loop this? That is 500 milliseconds divided by you are not doing that? No, how many times you need to loop this? This one. How many times you need to loop this? Everyone get not empty? You're not supposed to be that big. The bigger number is for the second exam. Okay, we'll make some minor changes here. The big loop is actually supposed to be for my second example. Okay, you all managed to get this? So this is your basic time block. If you repeat this basic time block for 250 times, you will achieve 0.5 millisecond. So in order for you to do this, you need to loop it 250 times, right? So what is the modification you need to make here? Now this one is a sequential thing. This 20 is a sequential thing. So this 20 instruction now we need to modify it so that we can use it in a loop. So when you do the modification, has how many fields? How many fields the Eclipse F has? How many fields? cycles, right? 20 instruction cycles give you the 2 microsecond delay. So we made some modification. From here to here is 17 NOPs, which gives you 17 instruction cycles. This one, this decrease will take 1, this branch will take 2. So 17 plus 1 plus 2, 20. So you have total of 20 instruction cycle here. But this 20 cycle is together with the loop here. So you see, move literally loop well. Loop value is 250 and you load it inside loop count, which holds the loop value. So you're going to repeat this 17 and then you're going to decrease loop count. This is skip if 0. So if it's 0 means it will go out of the loop. If it's not 0 means it will branch again. So one time the content of loop count is actually 250, right? Decimal. So how many times this whole loop will go? 250 times. One time takes how many cycles? One time it goes down like this.
20.
So how long is this? 2 micro. If you do this 2 micro 250 times,
0.5 waves.
yes, you get 0.5 millisecond. So this is how
요, 오늘 우리 뭐 이렇게 알이 있냐? 이렇게 내가
Sorry about that. Do you understand this? Do you understand the flow? So what we are doing now is, we have just written a program, an instruction sequence which will generate the 0.5 millisecond delay. When you execute this, the time that it takes from here to here is actually 2 microseconds, and because we are looping it 250 times, it will become 0.5 seconds. So, of course you may ask, so what's the big deal with this delay? So later on when you go to chapter 4, you're going to create a subroutine. You're going to create a subroutine, and in that subroutine you're going to put this program inside the subroutine. That means that subroutine will be known as the delay subroutine. So what you can do when we go to chapter 7, we'll be dealing with how to interface with external devices, for example like LED switches. So what you can do is, you can turn on one LED, you can call the subroutine delay. What happens when you come to here? When you come to subroutine, this program will run for 0.5 millisecond, and then you can turn off the LED. And then if you want, you can call the delay again, and then it turns on. So what happens? Every 0.5 second delay, it will blink. Do you understand? So later we're going to see the application on how we're going to apply this. But for now, do you understand how we did this? So just now, Nathan was asking, this 2 microsecond, is it fixed? No. You can choose whatever value that you want. So if you choose a bigger number here, what do you think happens to the instruction? If you choose a bigger value here, what will happen to the instruction? So when you change that, the larger that this basic time blocks become, the lesser you need to do. I mean here. Here. So the larger you choose, it will become less. Here the more value you go, the higher, right?
The bigger the value should be.
Higher cycles.
is 0.5. 0.5 millisecond, you divide with 100 nanoseconds. Okay, Alman asked a very good question. So why are you complicating life? Why need to create a basic time? So 2 microseconds, then from there you actually multiply 250 times, then only you get the 0.5 millisecond. So Hasman asks, why don't we straight away we put 0.5 millisecond and divide by this one? So what do you get answer? Yeah, what's the value? So that's supposed to be the second one. Yes. Another one, if he said if you use 0.5 millisecond, because at the end of the day we are actually dealing with one instruction cycle, right? We're interested with this. So he's asking why not straight away you divide this one, you get 5,000 instruction cycles. You need to have 5,000 instruction cycles. So which means this one how many lines you need to have? 5,000. 5,000 cycles here. In this what modification you need to do?
4,097.
You're not buying lah. 5,000 you cannot do here. You can't do 5,000 here. This is because there is a way of doing it. Show it a second. I have not come to that part yet. So this is the one technique of doing it. We'll come back to that later. So why bigger number cannot is because the loop count can only hold a value of 255 at one time. So if the number, if you need to loop it more than that particular value, you cannot sustain it. But there is a way of doing that. We will do multiple loops. But before we go into the multiple loops, see this one. This NOP, you're actually repeating this 17 times, right? So if you type this 17 long times, it's actually quite a hassle. So therefore, this NOP, what you can do, you can actually create a macro. Can you see in the notes? This is the instead of writing very long 17 instructions, what you can do is you can create a macro. This is the macro. We call it the duplicate and no operation macro. So this macro is fixed. This macro is actually fixed. Do you see that this macro receives an argument? This macro actually receives an argument. So when you type this coding, you must type as it is. This is fixed. Something you can memorize. Alone. So where do you write this macro? This macro you should always write before the program start template. So you write this macro before the program start template. So how your program will look like is that so the duplicate no operation macro will be here. Macro, and then you have your program start template here. Then this is where you have your main program, right? So instead of writing the NOP 17 times, you just need to do this duplicate no operation. See, this one receives an argument. So how many times you need to write the duplicate operation? 17 times. So you pass 17. And then this part is the same. Decrease file registers, skip if below. Okay. So this one takes 17 cycles, this one takes 1, this one takes 2. Total 20. How long does 20 take?
20 is 2 microseconds.
2 microseconds. And if you repeat 250 times? Oh, sorry, this one I missed something.
You didn't count.
From starting is the same. This one you should load the value to look count first. And then you call the duplicate operation. You pass the value 17 times because you will look 17 times. So what happens when you pass this? Yeah, let me just write this finish. So where should this again go? Again should come. Here. So this one is out. So this takes 17, this takes 1, this takes 2, total 20, gives you 2 microsecond delay. And if you multiply this 250 times, you get 0.5 millisecond. So when you call this duplicate operation in passing this argument 17, the 17 is actually received by KK, right? Then you declaring variable I, you declare I as a variable and you initialize the I to 0. While I is less than KK, what's the value of KK here? 17. You execute NOP. Then you increase by 1. So from 0 to 16 is how many NOPs? 17 NOPs. And then you end while. This is a while loop. While this condition is fulfilled, which means if I less than KK, when I becomes 17, it will no longer fulfill and it will go to end the macro. So how many times you execute the NOP there? 17 times. So when you write the main program, this instead of writing 17 times, 17 lines, you just can finish off with this one line. So this whole thing generates a 0.5 millisecond delay. Is there any question up to this point? Yes. It could be 1, it could be 2, or it could be 3. That's what it means. Huh? I don't know. Okay, one of the students asking why is the decrease it's actually in the instruction side is mentioned 1, 2 or 3 and branch also is 1 or 2. How do you know that this is 1 and this is 2? Because the textbook says so. It's mentioned that the decrease takes 1 and the branch again takes 2. Why it takes 1 and why it takes 2 I do not know, and it is not explained also in the textbook. So honestly I don't know. Why? Because it's mentioned like that in the textbook. Okay. Is that okay up to this one? Yes.
So is there a limit to how many times the counter can?
That's what I wanted to say. Like this now when we calculate 5,000 cycles. With one loop you cannot do 5,000 because the maximum that you can actually pass over the loop count is 255. So we will see in this next example. The next example. Now, are you all clear with this? So what we have just done is we have just wrote an instruction. This is actually our final instruction. We're supposed to generate a 0.5 millisecond delay. Is there any question on how we do this? Okay. Don't worry about writing. Make sure you understand. Is that question? Guys, you can tell something. Okay, if no question, let us try to play with some of the figures. What are the possible things that change? Physical could change, right?
Yes.
What if the question gives another frequency? For example, the question gives you 32 megahertz. What will change? The one instruction cycle duration will change, right? So what is the new value for 32? Does this change? Assuming that you always want to create a 2 microsecond delay basic time block, assuming we are sticking to this. So what do you need to change here? This one will come back later. So what do you need to change? This basic time block, because it's the same, so you keep it. So 1 to 5 nanosecond. So how many instruction cycles do we need? 16. We need 16. It becomes less. So this one I've showed you. This is how we design everything. 17 of these. So what are the things that we need to change here? This is still the same price. This one has not changed. Why? Because the basic time block you are still setting to 2 microseconds. So there's no change. You need to still loop that 2 microsecond delay time block for 250 times. But what changed? The instruction cycle required 16. So what should we write here? Yes, 13. You should write it 13. Always remember, the total number of instruction cycles must always minus 3. Why? Because of this fly and this fly. Always minus 3. So this is 13, 14, 15, 16. We have 16 cycles. And you loop it 250 times. This 16 cycle generates 2 milliseconds because this is based on 32 megahertz frequency. And if you do this 250 times, you get 0.5 milliseconds. Is that okay? Okay, oh, okay.
Okay.
Let us try to change something else. The basic time block. Different variable we are changing. So let's say, tell me one value. Tell me any value for basic time block. 2.4 or micro milli. You want milli? Now the basic time block that you choose is 4 milliseconds. Okay, let us stick to the 32. 125 nanoseconds. So if 4 milli divided by 125 nanoseconds, how many instruction cycles do you need? 32,000 instruction cycles. The problem is, you cannot pass decimal more than 255. This part here, duplicate operation. Because each time you're passing a variable, the variable value must be in 8-bit value. Because this is an 8-bit processor, so you can pass the data in one time of 8-bit length only. Which means this one also cannot be more than 255. So the maximum instruction that you can actually call is 258. Minus 3, you can do 55. That means you can send 255 here. Now when you do 32,000, this one will calculate. So that's why we need to choose a smaller base value. So that you will have a, okay, the rule is you must choose a base value when you divide with the one instruction clock cycle, you get a value which is less than 255. That is the rule. Of course, later we'll see an easier shortcut cheating. We'll see that. You understand? So that's why this one cannot. Because this is more than 255. So it's not possible for you to do the two-figure operation unless you are Rajin to type out 32,000 lines. Is that okay? So that's why we're going to do this. I purposely wanted you to choose some values so that we can see what is the limitation. So few limitations we saw. That this one, the basic time block, you can choose any value. That when you divide with the one instruction cycle, you get a value which is less than 255. That is one limitation. Another limitation is this one. This, how many times that you can loop the basic time block, this one also must be less than 255. If more than 255, then it will be nested loop, which we will see tomorrow morning. So let's choose another value here. Now someone say 4. Let's say 4 micro. 4 micro, how much again? Oh yeah, 32. Is this okay? 32 okay? Yes. It is 32 instruction cycles. Is that okay? That's fine. It's minus 3. So you'll get 29 here. So you need to pass 29 here. So just change this value 29. So this macro is the same. So you just put 29 plus 1 plus 2. Okay? 32 instruction cycles. Does this change? No. Still, you need to loop this basic time block 250 times. Is that okay? So we have changed two variables, right? One, the crystal oscillator. When the crystal oscillator change, what will change? The duration of one instruction cycle will change. The higher the frequency, the faster it will be. This is actually true. So which one is faster? This one is faster. 100 is faster. Don't get cheated with a number, a bigger number. Remember, in time, the smaller the number is faster. So 125 means it's taking longer than 100. You understand? So the higher the frequency, the faster it will go. Remember the oscillating signal. The higher frequency, what happens to the period? It becomes closer, right? Shrinks. Closer. It shows that the time is faster. So the higher the frequency, the time will be faster. The lower will be slower. So when this is affected, of course it will affect the number of times that the instruction cycles is required. That's why we did this example, right? If you change, it will become less. And then you just change this value. More or less, if you see this structure is the same. For the loop delay, this structure is the same. The only thing value will change is this value. This one. And another one we saw is, if you change the basic time block, if you don't want to use 2 microsecond delay, you want to use any other value, also can. The only thing will change is how many instruction cycles that you need. That's all. And you need to change here accordingly. So how do you actually get a good grip on this? Is by trying with different values. You can try with 20, 24, whatever frequency. You can try this here. Is there any question on this? Yes.
Just one question. The loop value and loop counter, right? What do we have to declare? Do we have to declare it?
Yes.
And if yes, what should we
This one should be on top of this.